Hi everyone, so today I'll be talking about how to calculate pH for strong acids and strong base. Before I get right into the formula, I'll define what a strong acid or base is. It just means their ions fully dissociates. For example, if I have HCl in an aqueous solution, it'll permanently dissociate to H+, Cl-. Likewise, if I have NaOH, it'll fully dissociate to Na+, and OH-. There's another terminology you'll need to know in that there are two different types of acids, and it refers to how many hydrogen ions it dissociates into. So for example, HCl is a monoprotic acid because it only releases one H+. But there's also a diprotic acid like H2SO4 that fully dissociates to two hydrogen ions. So it's diprotic. And this is all you need to know before we get right into the equations and formulas. Okay, so luckily the formula for calculating the pH of a strong acid is very simple. It's just negative log to the base 10, and you just need to have the concentration of the hydrogen ions. So when you have a monoprotic acid, they would usually give you the concentration of it already, then you can just substitute it in. But if it's diprotic, you have to remember you are releasing the double amount of hydrogen protons, so then you have to times that concentration by 2. If they don't give you the concentration of the hydrogen proton, just have to remember concentration is moles over volume, and volume is always decimeters cubed. So usually they'll give you enough information for you to calculate the concentration if it's not already given. Okay, so let's move on to the practice question and apply this formula. So please go ahead and pause the video and try to work it out yourself. If not, I'll go through the question with you. So the very first one is really just inputting what we just learned into the formula. But I think the first step you should always do is to write out the dissociation equation of the acid, especially because we have sulfuric acid right here, which is diprotic. So let's write this out just so you won't miss the fact that it's diprotic, because we have the concentration of the sulfuric acid, and we can see that the ratio between the sulfuric acid and the hydrogen protons is 1 to 2. So that means when you input the concentration into our formula, we will times it by 2 because there's 2 more. You can input this on the calculator because it is a calculator question, but you can also kind of work it out in your head, in that this is the same as 1 times 10 to the power of -2. So then the pH is 2. The next step is, this one's a bit more interesting because we are diluting the solution, and we're diluting it from original volume of 10 to a new volume of 100. And again, we don't need a calculator necessarily to figure this out, because if you can see, the difference of 10 to 100 is the same as 10 to 10 squared. So this tells us that the concentration of the H+ decreases by a factor of 10. And if you can recall from the formula, the pH is by a negative log of base 10. So since the pH decreases by 10, we know that the pH increases by 1 because the formula is negative. So the new pH is simply just 2 plus 1. So it's 3. Okay, so now I'll talk about how to calculate pH for a strong base. And technically, its formula is exactly the same as pH for a strong acid, because pH, you want to find the concentration of the hydrogen ions, which is what this equation does. However, when we see write down the equation of the base dissociating, we don't have the concentration of the H plus ions. We have the concentration of the hydroxide ions. So how do we find out the concentration of the H plus ions? And that's what I'll explain right now. So what we have to recognize is that water is actually very slightly ionized, which means that sometimes it will partially dissociate to its H plus and OH minus ions. Then we can write the equilibrium constant for this. So if you remember, Kc is the concentration of the products over the concentration of the reactants. However, the concentration of water is kind of considered as a constant because the equilibrium really lies far to the left. Like, it's really to the left of this reaction. So we can simply rewrite this equilibrium constant as just the concentration of the hydrogen ions and the hydroxide ions. And then there's like a special notation for this because this is specific to the ionic products of water. And they usually write its equilibrium constant with a Kw, like so. And then luckily for us, the IB lists out the different values of Kw at the different temperatures on table 23 of the data booklet. Which means, since we will have the information of the hydroxide ion concentration and Kw, we'll be able to calculate the concentration of the H plus ions, as the H plus ions is simply Kw over OH minus concentration. At 298 kelvins or 25 Celsius, Kw equals to 1 times 10 to the power of negative 14. And because of this, if you put 1 times 10 to the negative 14 into negative log 10, it becomes 14. So at this temperature, the pH of a base is actually just equal to 14 minus negative log 10 of the OH minus concentration. However, this is not always the case at every temperature because Kw is temperature dependent. So you can use this in exam 14 minus the concentration of OH minus ions, but I think this is what I'll write down now is a better formula because it'll work at any temperature. So at any temperature, and it is negative log 10 Kw over H minus. There is also another equation that could also be helpful. That's also helpful in calculating pH and pOH, which is that pKw equals pH plus pOH, and because of, this is why, I explained it a bit wrong, but it's because of this, this formula, why 14 minus pOH works when you're calculating the pH of a strong base, and it's because to find pKw is the same as like negative log 10 kW. So if you put kW in negative log 10, you get 14. So then pH is 14 minus pOH. So yeah, that's actually the explanation for this formula, but I recommend using this formula over that one because this one will always work. Okay, thank you for listening.